I welcome my viewers to another lesson on NMR Active and Inactive Nuclear Species. NMR stands for Nuclear Magnetic Resonance. It is a physical phenomenon and a spectroscopic technique that analyzes the properties of atomic nuclei to determine the structure and properties of molecules. Nuclear magnetic resonance spectroscopy is a powerful and theoretical, complex and analytical tool. It is important to note that with NMR, we are performing experiments on the nuclei of atoms and not the electrons. The chemical environment of a specific nuclei is deduced from things about the nuclei. In nuclear magnetic spectroscopy, nuclei with a non-zero spin are considered NMR active, while those with nuclei with a zero spin are said to be NMR inactive. NMR spectroscopy is widely used in chemistry, biochemistry, and medicine to identify molecules, study their structures, and monitor reactions. In the course of this lecture, proper explanation will be given on what we mean by NMR active and inactive nuclei. Don't forget to like, subscribe, and share this video with your loved ones. Note that subscription is free. Key concepts. Each nucleon, that is proton or neutron, has spin equals to half. Like electrons, nucleons are fermions and each has intrinsic spin of half. Total nuclear spin results from vector addition of the spins and angular moments of all protons and neutrons. Even numbers of protons and neutrons usually pair up, cancel each other's spin, often resulting to zero spin. Odd number of each proton or neutron has one unpaired nucleon, which determines the nuclear spin. How a spin of 3/2 arises. A nuclear spin of 3/2 arises when the nucleus has an odd number of nucleons. So one is unpaired. That unpaired nucleon, usually in a specific energy level or orbital in the nuclear shell model, has total angular momentum of 3/2. This includes both spin and orbital angular momentum. Example is sodium-23. It has 11 protons and 12 neutrons, so odd number of nucleons, so unpaired proton. The unpaired proton occupies a nuclear orbital with total angular momentum of J equals to 3/2, so the nucleus has a spin of 3/2. NMR active nuclei characteristics. Nuclei with a non-zero nuclear spin, I not equal to 0, are NMR active. Nuclei with an odd number of protons or neutrons often have non-zero spin, so are NMR active. Odd numbers are integers that are not divisible by 2, 1, 3, 5, etc. Even numbers are numbers that can be divided into 2 equal parts without a remainder, 2, 4, 6, etc. Nuclei with unpaired protons or neutrons can exhibit NMR activity as the spin of the nucleons are not fully paired, resulting in a net non-zero spin. These include nuclei with an odd mass number, hydrogen, proton, carbon-13, fluorine-19, phosphorus-31, or an odd atomic number like nitrogen-7. Table 1 here shows the atomic mass, atomic number, and NMR activity. Looking at the hydrogen proton, it has odd atomic mass of 1. It has 1 proton and 0 neutron in the nucleus. It has an atomic number of 1. The 1 proton exhibits the spin, so it is NMR active. We have another example, nitrogen 14, with an atomic mass of 14 and an atomic number of 7. It has an even atomic mass. It has 7 proton and 7 neutron, and it has an odd atomic number 7. The unpaired proton determines the spin. Carbon 13. Carbon 13 has odd atomic mass of 13 and an even atomic number of 6. So in the atomic mass, it has 6 protons and 7 neutrons. In carbon 13, the unpaired neutron determines the spin. We have NMR inactive atoms. The nuclei with a nuclear spin quantum number of I equals to 0 are NMR inactive. These nuclei have an even number of both protons and neutrons. Examples are carbon 12, oxygen 16, sulfur 32. If A and Z are both even, the nucleus is typically NMR inactive. We know that A represents the mass number, Z represents atomic number, and X represents the symbol of the element. So let's look at table 2. Let us look at these examples. We have here carbon 12. Carbon 12 here has an even atomic mass, and it has an even atomic number that can pair itself. The neutrons and the protons can pair themselves, so it is NMR inactive. It applies to oxygen 16, sulfur 32, and neon 20. The examples we have here are all NMR inactive because their atomic mass and atomic numbers are even, and their protons and neutrons can pair themselves. Let us look at isotopes of hydrogen and their NMR activity. Table 3 here shows isotopes of hydrogen and their NMR activity. We are looking at the protium, the deuterium, and the tritium. The proton, it has 1 proton, which is an odd number, and it has 0 neutron. So its nuclear spin is half. That is the spin of the single proton in the nucleus. It is NMR active, so we give it the symbol of good. The deuterium, it has 1 proton and 1 neutron, which are both odd, and it has a nuclear spin of 1. So in deuterium, the spin of the proton and neutron couple in a parallel manner, that is half plus half plus half, resulting to 1, and it is NMR active. So it is given the symbol of good. Tritium. In tritium, it has 1 proton, odd, and then it has 2 neutrons, even. So the nuclear spin is half. The spin of the neutron cancel each other. The nuclear spin is the spin of the proton, which is half. So it's giving the symbol good. All isotopes of hydrogen are NMR active. Isotopes of oxygen and their NMR activity. Table 4 shows the isotopes of oxygen and their NMR activity. We have oxygen 16, oxygen 17, and oxygen 18. For oxygen 16, we know that it has 8 protons and 8 neutrons in its atomic nuclei, and they are both even, so they will cancel out, and their nuclear spin will be equals to 0. So oxygen 16 is NMR inactive, represented by S. We have oxygen 17. It has an even 8 proton and an odd 9 neutron, and the even 8 proton we cancel out, while the odd 9 neutron, 8 of it we cancel out. It will be left with 1 neutron, which will determine its nuclear activity. So the nuclear spin is 5/2. Oxygen 17 is good for NMR and magnetic resonance imaging, giving the symbol of good, showing that it is NMR active. We have the oxygen 18. It has even 8 proton and an even 10 neutron. And they will both cancel out. Both the 8 proton and the 10 neutron will cancel out. So its nuclear spin is 0. It is represented by S, showing that it is NMR inactive. We have shown here how the 8 proton and the 8 neutron cancel out. If a proton has plus half and a minus half, they will cancel out and it will be 0. Opposite spin of proton cannot cancel opposite spin of neutron, or nor vice versa. We know that the nuclear spin is equal to the spin of proton plus the spin of neutron. Look at the isotopes of carbon and their NMR activity. We're looking at carbon 12, carbon 13, and carbon 14. Carbon 12 has even 6 proton and even 6 neutron, just as we said, that it will cancel out. So it will have a nuclear spin of 0. The spin of the proton will cancel out. So also the spin of the neutron. So the nuclear spin will be 0, represented by X. It is NMR inactive. Carbon 13, it has odd 7 neutron and an even 6 proton. The even 6 proton will cancel out. For the odd 7 neutron, 6 of it will cancel, and then it will be left with one neutron, which now determines the nuclear spin of that element. So its nuclear spin is half, and it is NMR active. Carbon 14. Carbon 14 has 8 neutron and 6 proton. So the even neutrons will cancel out. So the even protons will also cancel out. So it will have a nuclear spin of 0. It is NMR inactive. Study questions. Find the number of proton and neutron in the following atoms and their nuclear spin: nitrogen 14, nitrogen 15, and phosphorus 31. What is the nuclear spin of a proton? What determines the nuclear spin of an atom? Don't forget to like, share, and comment on this video. Subscription is free. We have come to the end of this video. Thank you for listening to the end. Please like and subscribe to my channel. See you in the next class.